Hi, everyone. We're running a little bit late. Your session chair is having trouble getting on. So I'm going to kick off the session. And so as a result, I'm going to apologize because I'm not even sure who the first paper is. Who is the first paper? Birthday? Is that how you say it? Kind of. You can correct me in a minute. So I will kick off the session, first of all, by saying hello. My name is Larissa Tokarczyk, and I'm a senior lecturer at Queen Mary, University of London, and part of the program committee for iLRN. We're going to have a session this evening. And just to remind everyone that it is being recorded. With that, I will hand over to the first speaker to pronounce her name much better than I will. Perhaps she can tell you a little bit about her background and what it is that she's going to present.
Okay, so I hope you see the first slide. Hi, I'm Birte. It's a hard to pronounce name from Germany. Me and my co-author Ulrich Schröder, we are working on a VR classroom, and we will show you today something about learning analytics and computer science in the VR classroom. I'll start with a teaser image. That's the normal setting, how we use the VR classroom. So you can imagine I am the person being the teacher and trying to stop Leah from sleeping in this picture. There is another person, it's a coach. He's able to let the students interact and let them throw paper balls and destroy me as a teacher. And as a teacher, we can learn, for example, classroom management. It's a project which got huge. It started at the University of Potsdam. You see, I'm not from Potsdam, I'm from the RWTH Aachen. We got inside of this project and got partners. And later on, more partners followed, not only universities, but also teaching training centers from Germany. And so you can also imagine that there is work done so far with so many partners. We started with dealing with disturbances. We got to dialogues in history classes, so how to enhance students to talk in your history class, security and chemistry classes, and how to start a lesson. And actually, we are enhancing the VR classroom for teaching of foreign languages and how to use media in classrooms. That's not the only pillar. We also have research, and we did research on the influence of presence and psychological stress reactions. As you can imagine, it's easy to overflow with ideas for this VR classroom, what to put inside, what should students be able to do, what you as a teacher should be able to do. And that's why in many places we try to work us through the ideas with the theory first method. And that's something I will show you today, because today it's about theory first. We checked what should we integrate in the VR classroom. So we started with observations. One observation is that a lot of our teacher students tell us teaching computer science feels different to other subjects. It's different because, for example, they have the feeling the students, they are hidden by the monitors and you are not able to directly look at them. And with that, we came up with the question, is teaching computer science different from other subjects? And if yes, why? And if yes, should we integrate a computer room in the VR classroom? The next observation we made is that reflection is important in learning classroom management. It's so important to think about what you did in class and why and how you could react. And for me, as a group of learning technology persons, we are directly there with the idea to use data and to support this reflection with learning analytics. And lastly, we had the idea to connect both of these and to have a cross connection between us as researchers and the teaching students. And so we thought about how can we make this informal observation and hypothesis explorable using learning analytics. So let's come to the first question. Is computer science teaching different from other subjects? If so, why? And we did a literature research. And to cut it short, yes, it is different. There is not that many literature as we initially thought, but we found some of the differences are already shown. For example, that we often use project-based teaching methods in computer science, and we often have such an interdisciplinary nature, just to name two of them because of time, but you can check the paper if you want more or ask me later. And the result is a classroom with computers in it. We have two different settings which are typical for German classrooms. Nowadays, I think they will change. We will have a lot more laptop classes, I guess. But till now, having normal computers is the standard in German schools, and having such a room. Here is another angle, so you can see some of them are programming in Unity. They program themselves. And sometimes videos show more than pictures. This is me looking at them when they are programming, and on the right side you can see that we have different options what we display at the monitors. Everyone can add whatever he or she likes, and there is some students programming in BlueJ. The second question was, can we support learners with learning analytics? It's not the best research question because it's a yes and no question. So cut it short, yes, we can support them, but the interesting question is how can we support them? And because you already heard, the observation was that some of the students told us that monitors, they give the possibility for the virtual students or for real students to hide themselves from teacher view. We thought we should check eye tracking. So we focused on eye tracking first. And we also checked the literature here, and we found that real classroom experiments already showed that novices and experts, they have different visual patterns. Novices tend to look at their teaching material, at the surroundings, the environment, and experts tend to focus more on the students and their behavior. We also found that there is a connection between the focus of the teacher and some facial attributes of the students, for example, gender. And lastly, and that's really interesting, that the focus of the teacher has an effect on students' learning. So together with the first novices versus experts, it's really interesting to see how a novice proceeds to be an expert and when it changed and how. But all of this was done in real classrooms. So we only had every scenario once, and the studies were not that huge as we like to have them as researchers. But putting all of this in VR, great, because we can let them do the same again and again. We can use the same scenario for every teacher to check if there is a real difference between novices and experts, for example. And we can use many more data. We can use the how they move their head, if they are nodding when a student answers, and how they walk around in the classroom, what they are saying, and eye tracking. So all in all, yes, we can support them. And now let's check how we can make this our insights visible. And we started with implementing something for the eye tracking part. And here are the results. For example, it's a heat map visualizing how often the teacher-student looked at the virtual students. White students were never looked at. That's a pity. But the red students, they are focused often, and the green students somehow, sometimes, and in between. This is another visualization we created to test later. It's also a heat map, but we can see more details of the students, but it's harder to distinguish the colors. It's from blue to red. And if you never looked at a student, for example, Anna or Moritz, they will not be colored. And Harald, for example, is a student I looked at, the participant looked at somehow, and George was one of the active virtual students waving hands and got in the focus often. Here's another visualization of this where you can better see Steve, who's not looked at often, never. We asked some participants from computer science if they liked the visualizations and if they were easy to understand, and all of them replied yes, but we don't count this as real evaluation because we asked computer scientists and not teacher students, and it should be intuitive to teacher students. And we also created some visualizations for us as researchers. Maybe some of them could be helpful for teacher students as well if they want to go into details. For example, this one, you can see the relation between the students' disruption. So if they throw paper balls, they may have a long blue line. And we have in green the time where how long the teacher looked at them in the whole situation. So Moritz, he was able to distract other students quite a long time. And we also asked our participants and some educators if they like the visualization, and they also said yes. Okay, and nearly last slide, and I'm running out of time. We started with the observation. We identified some questions. Today, I showed you the research and the implementation part. And the next thing we will do is a huge evaluation, as huge as possible. And we will hopefully start with it in the end of this month. And that's it.
Thank you very much. Actually, I was prepared to give you 3 extra minutes because of delay in starting, and I apologize for being late because I simply could not find the Zoom link. It sounds so old school of me. Birte, you were great. Thank you for accomplishing all of this. There is already some feedback on the chat, and so we now have like 5 minutes for questions and debate until the next presentation. I was just wondering if anyone would like to start with the questions. For instance, Brighton Yalka, you said this looks amazing. Any further feedback beyond that? I would like to I'd like to ask to help start. I'd like to ask whether you would consider this not just to support this analysis afterwards, but as like a way for constant feedback so that the behavior could change on both sides, on the teacher and pre-service training, on the students, if there could be some sort of instant feedback to for continuous change, behavior change?
That is a really good question, because we discussed it often. If we want to change this situation and enhance it directly while it's happening, and we decided to not change it, because in the real classroom the teacher will not get live feedback of what they are doing. But we have this guy, you missed the really first slide. There is another person sitting there and using a website to control students. So there is a mixture between automatic feedback of the virtual students. So if you are, for example, standing nearby, they will stop doing destructive behavior. But the coach, for him or her, it could be really helpful to get feedback what the teacher student, for example, is able to see. So because interacting in a classroom, it's so non-verbal sometimes, because maybe you just look at the student and you're like, I see what you are doing. So it could be so helpful for the person sitting on the computer and interacting with the avatars to know maybe what the teacher student thinks, and if he or she was able to spot the student, for example. So this is something where we want to include the live feedback.
We do have another question here on the chat, which I'll read. But before, I'd just like to give a preparation request to Francis Cambili Mzembe and Neil Gordon, who are the next ones. Just get your presentation ready. And so, Brighton Yelke asked what platform you are using for the visualization.
The visualization itself is done in Unity, and for storing the learning analytics data we are collecting, we use Learning Lockers or a typical learning record store using XAPI statements.
Oh, that's great. I'm using the same approach with XAPI because we actually have an initiative. We call it Invenira, where we basically say that these analytics from these activities should all fit into larger objectives, so that you could try and track your goals and objectives across multiple activities. So in XAPI, it's exactly what you're using too. So it's a very good thing that more people are using it. So it is. So Birte, it's Birte, right?
It's hard for international conferences.
Never mind, I'm doing my best. Sorry. So Birte, thank you so much for all your work. I'll now pass on the baton to. So who will be presenting? Francis or Neil, or both?
I think primarily me is Neil, then Francis can join in as well. Okay,
so please share your screen. You do have so you have this time slot allotted. I'd like you to do just like Berta, to have like 15 minutes tops with presentation, so that we can actually discuss and engage on this. So whenever you will, please. Can you find the share screen button?
Yes, should be sharing.
Yeah, there you go.
Sharing.
Oh, fine. It's working now.
Okay. Right. So, hello. Good evening, UK time. I'm Neil Gordon, reading computer science here at the University of Hull. This is some work with colleague Dr. Francis Cambili Mzembe. He's now based back at the University of Malawi. This is work that he did for his time here at Hull as part of his PhD. I'm just looking at this sort of a portable user cross-platform VR for school teaching, particularly in the context of Malawi, but as we'll see more broadly too. So looking here in this this presentation about the evaluation of this system. So a lot of overlap actually with previous talk, some of the technologies. The focus for Francis and myself was looking at this is more of a self-contained system though, that's got multiple users, primarily using off-the-shelf technologies and devices. We're looking at some of the challenges that are faced in certain contexts, and I'd say in this case in Malawi. So looking at how VR technology can help address that. So I've seen VR technology for a long time now. Here at Hull, there's been a research into sort of VR technologies for a couple of decades. But what's been so amazing to see in the last couple of years is that evolution into more domestic off-the-shelf technologies, but it's still really seeking that kind of killer application. Some of the things we're looking at is how can you use that in a place where that makes a lot more requirements. So the aim is looking at how we could potentially improve secondary school education in such situations. Or again, as in the previous talk, as computer scientists, we weren't looking to assess improvements in education itself. It was more looking at what's the possibility it could offer. So one of the things looked at was talking to teachers, what would they require, looking at the kind of context of use. So seeing, is it viable to use, rather than is it actually better at teaching? So there's a different issue. So what we're looking at was how the system could be evaluated in practice, how viable this is, potentially for use in secondary school teaching and other contexts as well. And part of the context of this, obviously, in VR education, I think in this sort of environment where the audience are all using VR, accept the value it has, potentially it has. But I think in wider education context, there's still a lot of people wondering how valuable is it for what it's really offer. So it's still really seeking a big uptake of use. So whilst there's a lot of acceptance that VR, augmented reality 2, XR in general, have lots of potential, I think one of the challenges there is how you make it seen as really useful in a way that's not just seen as maybe a gimmick. And very benefits for education from using VR. Some of that unique to VR itself. It gives you a different user interface, different environments. The kind of things which are flagged up with VR being helpful for education, things like the ability to repeat learning, but particularly in this immersive environment, so where you can give students access to spaces they couldn't usually access easily. Now, the work in this talk is from a follow-up to work presented at last year's conference by Francis, where we're looking at the implementation of the VR system. And in this session, we're looking more at the practice of using it and some evaluation of using that. And some of the things that I think got shifted as the research was going on was what the real benefits were and what the focus of it should be. And a big part of that was the multi-user, multi-platform idea. So the practicalities of this, the context, technologies and the devices that we use for the setup, they've chosen to account for technology and the issues that are faced in Malawi. So I think every country has its own different issues and challenges. But in particular for many countries, and Malawi is an example of that, the big challenge is things like relative poverty, access to equipment, financial constraints, access to ICT resources, access to the internet, and of infrastructure aren't a given. One of the big challenges that Francis is going to talk a bit about later on at the end in the Q&A part in particular is around the access to electricity. So here in many Western countries, in the UK, we expect electricity to be reliable and kind of always there. It's just a resource that's expected. So in Malawi, and many countries in African subcontinent and other places around the world, access to electricity isn't a given all the time. People get used to living with unreliable internet, unreliable electricity, and how you manage around that. One of the things the research was looking at was how could we build a solution which would then be viable in that sort of context. Again, the kind of some data that's in the paper that was in Francis' thesis. For example, nearly 1 in 5 secondary schools have access to electricity. Those that do have reliable electricity. It gives you an idea of some of the practical challenges these schools face. But equally, there's a big interest in technology. Again, some of the drivers for this research was the requirement by Malawi government to try and look at how they could use technology and improve things education-wise through technology. Mobile phones, battery-powered solutions are ways to enable access when the mains electricity isn't always available. Now, one of the big features looked at in terms of using VR for education was the kind of the why, like again the killer application aspect of it. So part of that was thinking about collaboration. So VR as an immersive environment has some benefits, but where it's really beneficial for education can be where people can interact together. So that kind of potential was seen as one of the big drivers of this work. Equally, one is trying to avoid being tied into one platform. Of course, could show things with a single solution, show kind of proof of concepts. There's in ways that we could do this that would be viable and practical in actual practice. So making it as widely useful as possible. And again, some of the work at Site and Paper, but if you focus on a specific device, it can limit who can use that. That's in terms of both access to the device itself, but also things like accessibility and inclusivity. Some people prefer or require certain sorts of device. If your solution was purely based on, for example, a VR headset, that would have problems with people who couldn't use that. Equally, if you rely on a certain sort of interface, tablet type interface, or a games controller, for example, again, it might limit certain people. So the idea was to find a very flexible approach that would maximize access. And so part of this was driven by wider context. One of the big contexts of this was global challenges. Something we look at a lot here at Hull is around sim development. Again, one of the driving factors in this research from the start was how could we use computer science approaches, computer science solutions to build technologies that could address UN goals, in particular in this case, Goal 4 for quality education. So in last year's paper, as I said in the proceedings from last year, you read about the design of the system, the implementation of it, but essentially what Francis put together was an interactive environment using VR. It was using a standard kit, so it got Oculus VR headset, and also Windows tablet, Android tablet, along with a Wi-Fi router to enable these devices to interact together. So you can see on the slides a picture of the kind of kit. Yeah, one of the nice things of that solution was Francis could fit it all in a single bag to carry. So you've got 3 potential interaction devices there, along with the routing device. Again, the idea was to try and find a way we could build a mobile classroom in principle. So to allow for some of the context challenges, flexible use functionality, competitive VR, use that work at the local network through the Wi-Fi router. Because of that, it didn't require direct access to the internet. The machine was configured, he set up the software so that the one device could act as the local host effectively for the VR interaction. The device is communicated via the Wi-Fi router, so you could use it in any location that you could actually just unpack it, switch it all on, and get going. And again, I mentioned the electricity challenge in Malawi context and some countries. All devices were based on batteries. Wi-Fi router usually uses a battery pack to plug that into, so that the entire system didn't require internet or network access locally, didn't require mains electricity. It gave you a full VR environment, but in a very mobile, portable, use anywhere kit. So that was the sort of platform itself. In terms of evaluation, one of the things looked at was how best to decide was it effective. This was done using heuristic evaluation. There's overlaps there with some of the other talks today. again, the idea here was that rather than try and get children to use it, teach to use it directly, initially we'd explore it as a heuristic evaluation, with experts trying it, and exploring usability aspects. So is it going to be viable in principle? Later work will look at, is it actually effective in improving education? But certainly in terms of a VR environment and then access to this this kit and this interface, we're looking at, is it going to be viable to use? Are there any issues with that? So the purpose of this evaluation wasn't to look at the three devices in comparison to each other, but rather what's your overall experience of that collective platform. Data collection used so experts here in the UK, so 4 evaluators who've got various expertise in software development, VR, computer graphics and games to try out the solution. So this is based on heuristic evaluation. So Francis looked at some of the heuristic criteria, adapted for these to the ones that would be suitable for his particular solution. And so we've got these 10 primary heuristics and adapted them from Nielsen's scale to look at some of the potential acceptability of these different heuristics. So again, how good for systems are going to put feedback, clarity of use, consistency of use, etc. And then in terms of rating value, where these things purely cosmetic problems, or they go right through to say rating of 4, something would be very problematic for users. So usability catastrophe, as it was phrased. So anyway, also these systems then can allow the users to interact. So Francis designed, built this 3D environment, this sort of simple world you can see in the slide, bottom right picture. What's in here are 3 images from 3 input devices, 3 output devices. It's got the headset at the bottom, so 2 images left and right eye, and then the Windows tablet and the Android tablet to see the kind of views that different users would get. So they would have an avatar in there, they can interact in there. And this meant that you could set up a learning space and you could do various things in that space. And again, this was driven by that problem context. Even a place we may have a physical classroom with physical resources. Within this world that Francis developed, the users could then create, or teacher users could create a space, like a virtual physics lab, for example, and the students could then interact in there, do things that they couldn't do because they had access to a physical lab. But they could collaborate, work on problems, problem solving, exploring, learning. So the idea was to create this space where you could give access to things in a very usable way, using different devices. And getting
1 minute, Neil.
Okay, yeah, there you go. So analyzing the data, you can go to the index on that, look at the issues. So say in terms of 3 devices, we've got the evaluators' identification of major usability problems. Say Project A found only a couple of the Windows tablet, Project B only identified 1 on Oculus, Project D found a few on the different devices, C was maybe more standout, having several problems. And looked at the validity index of that, is that really a problem? And we've got these values of 0.5, 0.5 and 0.25. So to kind of conclude from that, for most of the major problems across the group of devices, i.e. the solution as a collective was fine. The only one was a major problem might have been on the Android device for user C, but they were quite happy to use the headset, which indicates again benefits multiple devices. Someone who's like one device could use another device, depending on your finances, what's available kit-wise. If it's mobile phones, tablets, up to headsets, you can use them all together. And so what we've shown from this is that with that school environment and the challenges of that context, we can make it viable for people to access a VR environment in a way that is, from a usability perspective, very usable. Thank you.
So thank you very much, Neil and Francis, who is also present. So we have now 4 minutes for questions because of the overlap of time. But if some presenter is shorter, we can try and come back to you. So I ask, while people prepare questions, that you can put them on chat or you can just turn on your microphones. I ask the next presenters, Anna and Zinta, who I see in the list of participants, to ready their presentation. And so, who'd like to make a question? This would be the time where I could try to raise the room. But let me tell you, I'm extremely interested because I am supervising several students from Mozambique, so right next door from Malawi, and they do have these concerns about what are the features to make this feasible. So one question I was wondering was, when I saw that you had the laptop there, I thought the laptop would be serving the virtual content, but that is not the case. So from which of the devices is the virtual content coming?
Yeah, I can answer that. So the way it was set up, you could do it from any one of the devices. So the idea is you don't need to have all the devices. So if you can't afford headsets, for example, right, you can just use maybe Android devices like tablets or mobile phones even, or if you just have like Windows computers, then you can just use those. So the idea is to be as flexible as possible. So any one of those devices could be used as a server or a host. So for example,
Yes,
during the
so
evaluation,
it's a peer-to-peer. Yeah, so it's a peer-to-peer network.
No, it's
What
actually
software?
it's actually a client server architecture. It's just that I was using Unreal Engine, so I used Unreal Engine to develop it. So so the engine uses client server architecture for that. But the idea is like any one of those devices could be a server. It's literally just a case of somebody choosing to be the host, and then everybody else joins their session.
Okay, so it's extremely flexible, and so that also means if it breaks down, or if it runs out of battery in the middle of the process, you can keep it going with the other one.
So there's a way. Yeah, so you can set it up so that the session can migrate to another user as a server.
That's fantastic. That's really nifty. So people, more participation. You are, if you cannot turn your microphone on, just tell me now. We do have a couple of minutes more. It seems not well, Professor Francis and Neil. I deeply appreciate your work, and I have already sent to my PhD students the abstract and told them to look this up. So if you want to cooperate with students in Mozambique interested in VR and virtual laboratories, also get in touch, please, because they do welcome collaborations.
I'll be more than happy to do that. Thank you.
Okay, thank you very much. And so at the exact time, I move on. So Anna and Zinta, who will be the first presenter? Any of you can come in.
Hi, hello.
Hi, Anna.
Yes. Hello,
So
yes.
you can share your screen. You can share your
Yes.
screen and start, please.
Sure. Yes, so we're both here today. Good evening from Latvia. It's already evening here.
Hello.
So, full screen. So are we ready? Yes, we can start.
Please do.
Yes, so hi everyone. Really excited to be here, to see you all. So we're from University of Latvia, Faculty of Education, Psychology and Art. And we would like to introduce you to our research framework for pedagogic and usability principles for effective multi-user VR learning environments. So as we see, especially in this conference, VR has a lot of potential in education, and the availability of standalone HMDs has supported the popularity of these technologies. And at the same time, there are still significant obstacles in the integration of VR technologies in education. And one of these is the lack of ready-made and easy accessible learning content. And for VR technologies to become an easy to use tool in higher education, it needs to be educators need to be able to create and edit content themselves. And to support that, it is essential to develop materials and guidelines that can guide and help to ensure quality of learning content and design. So one of the essential aspects that we are looking in is usability. Yes, we agree that success of VR in educational content depends in large part on how usable and adaptable it is in the learning process. So the objectives of our study were to identify what pedagogic and usability principles support effectiveness of VR in learning applications, and we wanted to propose a framework of these principles.
And yes, hello from Latvia. I'm Zinta, and now I would like to shortly introduce about our research background. And this study used Gagné's 9 events of instructional module and Nielsen's usability heuristics and the pedagogical principles of technology-enhanced learning. And this approach is based on the recognition that multi-user VR learning environments require through evaluation from both educational alignment and usability perspectives. And Gagné's 9 events of the instructional model provides a comprehensive framework for designing and evaluating instructional content, ensuring that it's aligned with specific learning objectives. Meanwhile, Nielsen's usability heuristics offer a set of guidelines for assessing the usability of digital interfaces, which is particularly important in multi-user VR environment where intuitive and user-friendly design is essential. And then incorporating this technology-enhanced learning pedagogical principles into this model. This emphasizes how important it is to design engaging, interactive lessons that are tailored to the needs and preferences of the learners.
Yes, so here you can see our students in action testing VR applications. So to assess the usability, the study used mixed method approach, which included VR content testing, as you can see here, as well as survey data collection before and after the user testing. Yes, so and also, yeah, you can see higher education students with different backgrounds, with different experiences, and yes, so the 2 surveys that were developed after the testing. The first one was to gain a deeper understanding on students' perception on VR in education, their thoughts about it, while the second survey included more specific questions regarding the learning process in VR and the feedback of their subjective experience of the tested apps and their evaluation on usability. And in addition, also 3 experts with experience in digital design and, of course, experience in VR technologies were involved in usability evaluation using Nielsen's heuristics. And they also tested the same 3 apps and evaluated them.
Yes, and here you can see our main findings said that 41% of the surveyed students stated that usability concerns they encountered might be resolved by providing clear instructions and user assistance materials, despite the fact that the tested VR environment supplied guides and instructions. There were still issues which arises the question of whether the instructions are helpful and how they should be communicated. And about this pedagogic perspectives, that none of the virtual reality multi-user environments presented an introductory module that could introduce students to the environment. and capture students' attention and provide additional motivation for learning. And none of the environment was aimed at a specific learning objective.
Yes, so the combination of Gagné's 9 events of instruction, aspects of TEL, and Nielsen's usability heuristics provides more through approach to evaluating usability and effectiveness of these applications. And usability, as we see, is one of the major considerations for effective adoption of VR learning applications. So to successfully incorporate VR in education, there must be a synergy between usability and instructional focus. So by considering both of these aspects, this framework can help identify areas for improvement and ultimately lead to creation of more effective and engaging VR learning environments. So in parallel, this framework can also be used as a tool for educators for evaluating VR environments.
And further research validating the proposed framework is recommended, including long-term framework testing and validation with larger and more diverse educator and learner groups. And also this phase of the study should include a validation of the framework with education and VR technology experts, as well as defining specific examples of how to achieve each principle defined in a framework.
Yes, so thank you very much for your time and attention. I guess we saved a little bit of time for the next presenters, and probably we have a bit more time for questions. Yeah, thank you.
Yes, exactly. Thank you so much. Thank you so much. I also have some yes, you saved 7 minutes. So we do have more time for questions and debate. I would like to ask you if you could put that slide with your framework a little longer, because as I was starting to read it, it went away. So yes, I must say that I made a mistake, and I now have from within the next hour, I have to be in 2 places at the same time, because I have to present at another. So I will be replaced chairing this session for the next paper by Professor Jonathan Richter. And I would like to ask Gianni Cotromanos, Ioannis Vrelis, Tassos Mikropoulos, and Tryphon Sivenas to prepare their presentation. Okay, Tassos, old friend, sorry, but I'm not going to witness your paper.
Okay. Is there some time for a question? Just one question.
Yes, there is plenty of time for questions now. Go ahead, Tassos. If you have
Okay.
for this.
So may I ask something?
Sure, yes, please.
Okay, thank you. Really nice work. 2 small questions. Why you have chosen Gagné's model, and is your framework Gagné's dependent?
Yes, thank you. Yeah, so the idea was we are really interested in diving deep into the usability, but we really didn't want to forget about the pedagogical side. So it was important for us to still find a framework that provides a really guide that could help us also incorporate these events that Gagné has presented, and so they also help to incorporate effective principles in the VR learning process, in the content.
Thank you. We have a question from Birte, who has raised her hand. Please, Birte.
I don't have a real question, but I wanted to encourage you to keep on, because recently I wanted to evaluate the usability of another VR application. I did not show it today, but and it was so hard to evaluate it, because on the one hand we had a diverse setup of students trying to use it. And on the other hand, I tried to find a systematic approach to evaluate the usability in a learning application. And I was not able to find something really useful. So in the end, it was qualitative and it was exhausting.
Yes, I can agree.
Let me see if there are any more questions. With no raised hands, but we do have some more minutes for questions, or we can start the next paper earlier. I would like to ask, I'm not sure if this was in your future work or not, if you are considering including or combining with this advice and principles, specifically considering the multi-user VR environment, because you have, this is for that environment, but then there are small details, right? That when you say that the environment must be carefully evaluated, the educator needs to choose the most relevant. But I was wondering, often when you start to do this kind of stuff, small details derail you. For instance, in my last session using the Oculus Quest, I realized I cannot take notes because I cannot see any paper to take notes. And so I had to prepare with this kind of complementary alternatives beforehand, stuff like this. So I was wondering if you are considering more practice related details in complementary about this.
Yes, definitely. Actually, it's already ongoing process. So we are trying to find practical examples how you can achieve each of these points. And we're doing that by asking education experts who actually practice every day and also use VR. So we want to compile this framework with more actual ways to achieve these points. And also one thing we are incorporating is eye tracking. So we were very excited for Britta to also share her experience with heat maps, and but that is probably for the next year.
Thank you very, very much. There is now some debate ongoing just about transparent headsets on the chat. Anyone else with more questions? So if not, we can move on to the next paper. But in this case, allow me to pass the baton of sharing to Professor Jonathan Richter.
George, Ionis, Tassos, you ready to go?
Yes, Jonathan, thank you.
Yes, sir.
All right, without further ado, please go ahead and the recording started. Thanks.
Lovely. Brilliant. Hello, everyone from warm Athens, Greece. My name is Tristan Sivenas, and it is my pleasure to present to you our work today with George Koutromanos, Ioannis Frellis, and Tassos Mikropoulos, that are with us in this Zoom session today, regarding teachers' experiences when using interactive applications with augmented reality glasses. According to previous studies in the research literature, augmented reality is an emerging technology that has got teachers' interest for, over a decade now. This is due to the fact that previous studies have identified a number of affordances, as you can see in the slideshow below. For instance, observation of invisible phenomena, information accessibility, as well as improved development of spatial abilities. The use of augmented reality in recent years expanded quickly. This is due to technological advancements in our mobile devices that basically allowed us to build and create a variety of mobile applications that are heavily based in augmented reality technology. This approach basically allowed us to explore several use cases of augmented reality in a number of fields, including, of course, education. However, even though we can safely say that, augmented reality has matured quite a bit in recent years, there are certain limitations. As you can see in the picture on your left, we have a smart device, be it a smartphone or a tablet, that has certain potentials and limitations. One limitation has to do with limited interactivity and immersion of the augmented reality content. On the other hand, we now have newer technologies that were specifically designed for better augmented reality experience, as you can see in the picture on your right. So basically, using augmented reality glasses, one will find an additional amount of abilities and affordances as well, including presence and first-person view. We investigated the concept of interactivity as well as immersion and its potential in education. It seems to us that interactivity is an important feature of augmented reality technology, and is considered essential for student engagement in constructing knowledge through learning by doing. Immersion, on the other hand, is the extent to which the user's senses are exposed to the virtual content, and is considered important in creating a more realistic and situated learning experience with augmented reality. However, when reviewing the literature, we actually found out that the majority of research focuses heavily in mobile-based augmented reality applications. So in layman's terms, this means that we have very few studies that focus on the use of augmented reality glasses in education. I would also like to emphasize how it is quite important. Well, the teacher is an important catalyst in the adoption of any technology in the classroom. So in other words, we could say that if a teacher has negative perceptions towards a technology, he or she will not adopt it in their classrooms. So moving on to the aim of our study. After identifying a research gap, the purpose of our study was to investigate teachers' experience regarding the use of immersive, interactive applications, well, with augmented reality glasses. We specifically examined, as you can see, 4 factors, namely spatial presence, simulator sickness, usability, as well as workload. Moving on to our rationale. So basically the rationale for selecting these factors was due to the fact that previous studies have highlighted how user experience is based on these exact 4 factors that I'll analyze below. The first one has to do with presence, which is the feeling of being there, really. Being inside the AR content. The second one, as you can see, is simulator sickness. This is a form of motion sickness that may occur when using a virtual or augmented reality environment. Well, if most of you have used virtual augmented reality applications, you may understand what I'm talking about. The third one has to do with usability, that measures how effective and efficient the system is. And lastly, we examined workload, that basically measures the cost for the human when accomplishing a task. So we did a literature review, and a detailed review of the research literature revealed that no previous study examined augmented reality glasses in teacher sample on the 4 factors I analyzed in the previous slide. However, we did identify 3 studies with certain limitations. The first study, as you can see, measured simulator sickness in aviation, medical, and space industry. This has nothing to do with education. The second one measured presence, simulator sickness, and usability in heating, ventilation, and air conditioning industry. The same pattern as well. So the third one had to do with an educational perspective that measured presence, simulator sickness, and satisfaction in university students with quite promising results. It's a very interesting read. However, we were actually unable to find a study that focused on teacher sample. As far as our research goes, our sample consisted of 46 in-service, primary and secondary education teachers. The majority of them, as you can see, were female, and below you can see their experience in teaching, as well as computer and augmented reality familiarity. As you can see, they were quite experienced in augmented reality. As far as our data collection goes, we used an online questionnaire that was split in 5 sections. Well, in the first section, we collected anonymized demographic information, and then we used adapted questionnaires of the 4 scales I've already mentioned, presence, simulator sickness, usability, as well as workload. So prior to collecting data, we had an activity where we had the teachers interact with Magic Leap 1 augmented reality glasses. Initially, the teachers came one by one. They became familiar with Magic Leap's controls and abilities, and then they had to interact with 3 interactive educational augmented reality applications. Data collection took place in our lab of the Department of Education of the National and Cappadocian University of Athens here in Greece. The average time for the teacher participant to actually complete the activity and file the question as well was about 1 hour and 20 minutes. So in the following slides, I'll actually present the augmented reality applications that we selected. The first one, as you can see, is called Dinosaur Kit. It basically allowed the teachers to create a velociraptor by dragging and dropping bones, as you can see in the picture. The second one was Figmin XR, that basically allowed the teachers to create virtual drawings. This was a rather interesting application. For instance, you can see on the picture in the presentation that we have a screenshot of a dragon that a teacher created during the activity. So basically, the teachers were able to interact and create their own designs. That was a really interesting approach. And the last application was Museum Alive. In these applications, they had to use hand gestures, and they could select a number of prehistoric animals, and they were able to see their animations and movement. As far as our data analysis goes, well, we used SPSS version 26, as you can see, and we measured Cronbach's alpha, as well as mean and standard deviation. Moving on to our results. The results of spatial presence scored relatively high, as you can see. It basically seems that the first two questions had the highest scores. This, in layman's terms, this basically means that the participants felt that the augmented reality objects they interacted with, they felt they were on the same place as they were, and they felt it could actually reach and touch them. The lowest score was noted on question 3, that basically asked the teachers if they felt they had to get out of the way of a moving object. This could be due to the fact that the teachers saw virtual moving objects, basically animals, in the third applications I discussed earlier. Moving on to simulator sickness. The results here are split in 3 clusters, as you can see: nausea, oculomotor, and disorientation. As you can see, the results are generally high, especially in standard deviation. However, we found similar results in research literature that could be attributed due to the fact that, well, most teachers felt no symptoms, while others reported intense symptoms. This may be due to their age or lack of experience. As far as usability goes, the results seem quite high. The majority of the teachers found that the augmented reality classes were quite easy to use, and they actually showed a positive attitude towards the use. And we did receive a quite positive informal response as well on them. Moving on to workload, the scores basically seem generally low. This means that even though the teachers felt that, well, the application required a reasonable amount of mental and physical demand, the overall effort was small, and the frustration seemed quite, well, minimal. So to sum up, this is one of the first studies that examined teachers' spatial presence, simulator sickness, usability, and workload of augmented reality classes. The results seem promising, exhibiting high presence, well, low simulator sickness, relatively low simulator sickness, high usability, as well as generally low workload. Oh, I'm sorry, I've actually moved one slide. Yeah, the limitations that were identified have to do with the use of convenient sample, and the fact that the conditions were lab-based and not real teaching conditions. Lastly, I'd like to point out how future studies could examine the use of augmented reality classes in real teaching. Oops, I have quite a bug here. Yeah, that's better. Yep, it's the touch screen. Sorry about that. So basically, we could actually do research in real teaching conditions instead of our lab-based situation. And this concludes our presentation. I would be more than happy to answer any questions that you may have.
Any questions? We've got some time since we started just a titch early. We've got like 8 minutes left. Actually, 12 minutes.
Yeah, I actually quite fast to it. Yeah.
You are. Any questions? I had just one thing. Trifon, is that your name?
It's Trifon, actually. And
Trifon,
it's nice to see you virtually.
I need to learn. Thank you.
No worries.
I was wondering, you said something about adoption earlier on, and I was wondering, just in terms of like that adoption cycle, I noticed that in your study that most of the teachers that were participants were fairly well adept at using AR.
Yep, that's right.
So they were already kind of onboarded, they were pretty comfortable with it, but
yeah,
just wondering what your thoughts on that adoption cycle. Yeah, go ahead. We chose this sample because we wanted to avoid the novelty effect. You see, when we actually introduce a new technology to users that were quite inexperienced to that technology, we may receive different results than the actual ones that were expected. So basically our sample had AR experience in terms of using mobile applications, not wearable technologies such as smart glasses. So they did have some sort of a background in augmented reality applications by developing QR codes as part of their coursework and using some sort of applications that, well, augment the environment using mobile phones and tablets as well. No prior use case on wearable devices, so no smart glasses used. Yeah, nice. Okay, yeah, because working with beginning teachers, they're
a solution looking for a problem, but they've already understood how it works, what kinds of things they want to apply it to, and the design of it matches a lot of those.
Yeah, that's right. The most interesting thing we noted when comparing these technologies, so basically it's the same technology but a different device, was that they had the movement. They were able to move in a place. It's quite difficult to move holding a mobile phone or a tablet. And the interactivity, as well as the immersion. The immersion, I don't really think it's comparable to having a tablet at hand and actually experiencing that feedback that you get from the smart classes. Yeah. And it's quite interesting times really that we did this research, since basically Apple announced that, well, they're proceeding with their augmented reality classes and they're due to I believe January of 2024, their newest date. So I do that it's a quite hot topic. Yeah.
It's going to be soon, right?
Yeah. We're actually expecting that. Yeah.
Yeah, very, very cool. And any other questions or follow-ups?
Yeah, we do. I believe we do have one in chat from Mr. Koutropoulos. No, they're not. They do not have to be tethered to the computer. So they do have some sort of a wireless experience. Keep in mind that we do have a controller that I may rush to explain the presentation. Yeah, yeah, but they're wireless. They're considered wireless. This is the best thing that technology has to offer right now. Well, until Apple offers their solution. Yeah.
Right.
Yeah, I couldn't really compare them to different technologies that use mixed reality, such as Microsoft HoloLens, that they're, well, wireless as well.
All right. Well, if there aren't any other questions, yeah, thank you very much. That was wonderful. Really interesting conversation.
Cheers.
Presentation.
Happy to be here.
Yeah. Shall we move to the next? Georgia Kazaku, teachers' perceptions towards the use of augmented reality smart glasses in teaching.
Hello, let me share my presentation. Okay, first of all, I would like to thank you for giving us the opportunity to present our work, and also congratulate the organizing committee for this successful conference. Dear colleagues, my name is Georgia Kazakou, and I am going to present a joint work made by me and George Koutromanos regarding teachers' perceptions towards the use of augmented reality smart glasses in their teaching. This is an ongoing work which is related to the previous presentation, as authors of both presentations are all members of the same research group. Recently, smart wearable technologies have been used in many fields, such as health and education, resulting in an increase of research interest. One category of smart wearables is augmented reality smart glasses. They are defined as a wearable device with one or two screens that can merge virtual with real information in the user's field of vision. They differ from other mobile devices, such as smartphones and tablets, due to their affordances, and compared to mobile devices, they provide a greater immersive and interactive experience. Augmented reality smart glasses have a variety of affordances, such as interactivity, representation fidelity, sense of self-location, immersion, hands-free access, and first-point view. Previous studies in the field of digital technologies in education have shown that studying the acceptance factors of a new technology in the early stages of diffusion can facilitate their integration in the future. Given that teachers are among the most important stakeholders for the successful integration of the augmented reality smart glasses in the education of the future, as they are for any other technology, we considered important to examine the factors that influence teachers' acceptance of the glasses in teaching. However, the research conducted so far has not enabled teachers to interact with augmented reality smart glasses and their applications. I would like to point out that this study is a pilot one and is part of a broader research aimed at the formation of an acceptance model for the augmented reality smart glasses by primary and secondary education teachers. The objectives of this study were the examination of teachers' perceptions regarding the use of the glasses in teaching, and the pilot implementation of a questionnaire for the acceptance of augmented reality smart glasses. In order to examine teachers' acceptance of the glasses, we had, of course, to review theories and models of technology acceptance. In the past, many studies have used them to examine the factors that influence pre-service and in-service teachers to use various technologies in their teaching. Examples of these theories and models are the theory of reasoned action, the theory of planned behavior, and the technology acceptance model. Of course, TAM is one of the most widely used models, which has been extended by adding social variables, resulting in TAM2 and TAM3. We also reviewed previous empirical research on augmented reality smart glasses in all applicable fields, including education. Since the objectives of this study do not include the results of that review, we are not going to present them today. However, we must exclude the field of education, of course, in which we found that 4 studies have been conducted so far. 3 concerned the higher education and were quantitative. The 4th concerned in-service primary and secondary education teachers and was qualitative. These studies had 2 common characteristics. They based their theoretical framework on the TAM, which they extended, and participants did not have the opportunity to interact with the device of augmented reality smart glasses. In addition, we reviewed previous empirical research on mobile AR, where we found a greater number of studies. Some of them are theoretically based on unified theory of acceptance and use of technology, and more research is based on TAM, which is extended by adding variables. One such case is the mobile augmented reality acceptance model, MARAM, which was based on the core variables of TAM, intention, attitude, perceived usefulness, perceived ease of use, to which they added 4 more: perceived enjoyment, facilitating conditions, perceived relative advantage, and mobile self-efficacy. So taking into account the aforementioned studies, our study used as a theoretical framework the MARAM and the social influence variable of unified theory of acceptance and use of technology. We chose MARAM, which is a recent model, because it was found to be valid for predicting the acceptance of AR by 2 different samples, pre-service and in-service teachers. The addition of the social influence variable was made because an individual's beliefs are shaped by both individual and social factors. Social influence is defined as the degree to which an individual perceives that important others believe that he or she should use the new system. As you can see, this conceptual framework is consisted of the 4 variables of TAM and 5 more. The first variable is the facilitating conditions, which is defined as the degree to which an individual believes that an organizational and technical infrastructure exists to support the use of the system. The second variable is the perceived relative advantage, which is defined as the degree to which an innovation is seen as better than the idea, program, or product it replaces. The third variable is the perceived enjoyment, which is defined as the extent to which the activity of using the computer is perceived to be enjoyable on its own right, apart from any performance consequences that may be anticipated. The fourth variable is the mobile self-efficacy, which is defined as an individual's perceptions of his or her ability to use mobile devices in order to accomplish particular tasks. And the fifth variable is social influence. Moving on to the method of the study, the sample consisted of 45 Greek in-service primary and secondary education teachers who were postgraduate students at the Department of Primary Education of the National and Kapodistrian University of Athens and had experience in using AR through smartphones and tablets. 40 of them were women and 5 were men. Teachers' years of service ranged from 1 to 33 years. We used the questionnaire consisted of validated items derived from MARAM and the social influence variable of Unified Theory of Acceptance and Use of Technology. This questionnaire was pilot tested by 4 in-service teachers. It was created online and consisted of 2 sections. The first concerned the demographics of the participants, and the second section consisted of 33 items for the 9 variables of the research model. Participants were asked to respond in a 5-point Likert scale. Regarding the procedure, the study took place in January 2023. We used the Magic Leap 1 device, and teachers used 3 interactive applications of the glasses. I'm not going to elaborate on these applications since we already have seen them in the previous presentation. So I'm merely reminding that the first application concerned the assembling of the bones of the skeleton of an extinct animal. The second had artistic content, since by using it, it was possible to create virtual 3D drawings and was the most enjoyable according to the teachers. The third application was related to the animations of 3 extinct prehistoric animals, maybe the most interactive one. For the analysis of the results, we used SPSS 26. In order to examine the internal consistency of the 33 items, we used Cronbach's alpha. Then a descriptive analysis of the data was conducted, namely the mean and the standard deviation were calculated for each of the 33 items. And now let's talk about the results. Table 1 presents the results of Cronbach's alpha for each of the 9 variables of the questionnaire. Most variables have values above 0.70, which is considered satisfactory, except for intention and facilitating conditions. Table 2 presents descriptive statistics of the items for the questionnaire. As you can see, most variables had on average relatively high means, above 4, meaning that the teachers of the study had positive scores for these variables. More specifically, teachers intend to use the glasses, they have very positive attitudes towards their use, and perceive them as easy to use. They also perceive them as a useful technology and as a technology that has a relative advantage. For instance, they perceive the use of the glasses as a means of offering new learning opportunities compared to other mobile devices, smartphones, and tablets. Regarding the facilitating conditions, teachers may feel that they have the necessary resources to use the glasses in their teaching, but they do not have the knowledge, the time, nor the necessary support from the school to use them eventually. Also, teachers perceive the glasses as a very enjoyable technology. Teachers' perception of their self-efficacy about using the glasses in their teaching is relatively positive. Finally, in terms of social influence, teachers do not seem to feel a strong pressure from significant others to use them in their teaching. Discussing the results, we must underline that teachers are positive about the use of the glasses in their teaching. On the contrary, they had fewer positive perceptions towards facilitating conditions. This fact reveals that in order for teachers to use augmented reality smart glasses, they need to have all those conditions that can facilitate them to do so: devices, training, and support. The results also showed that teachers had a low mean in social influence. This finding means that they do not feel pressured by their environment to use the glasses. Perhaps since this is a technology still new, the teacher's environment does not perceive its value yet. Moreover, the examination of Cronbach's alpha showed that the reliability of most variables was high and acceptable. In contrast, the value of Cronbach's alpha for intention was low. Future research will have to examine whether the three items of intention, I intend to use, I plan to use, and I predict to use, that have so far been used for the acceptance of many technologies through TAM, are also suitable for research on the acceptance of the glasses in the field of education. One possible solution is for the intention variable to be examined by adopting other items that have been used in more recent research with immersive technologies. For example, an item, I would use the glasses again if given the opportunity, could provide different results in measuring teachers' intention to use the glasses compared to the items that have been used in this study. Cronbach's alpha was also low in the variable of facilitating conditions, perhaps due to the differences between the teachers in terms of education or the education level, teaching subjects, computer equipment, and technology. Of course, the study is not without limitations. A specific smart glasses device was used. It may be that using another device would lead to different results. Also, the sample had experience in using AR via mobile devices. Finally, further research is needed to enhance Cronbach's alpha in the intention and facilitating conditions. Moreover, this study needs to be extended by measuring the proposed questionnaire to larger and more representative teacher samples to develop an acceptance model for augmented reality smart glasses by primary and secondary education teachers. It will be useful to include in this model variables that will measure the affordances of the glasses and whether they affect teachers' intention. Such affordances include immersion, presence, interaction, and engagement. Thank you very much for watching our presentation.
Excellent, Georgia. Very nice.
Thank you.
Do we have any questions from the audience? Let me look in the chat. I don't see any in the chat. I had a bit of a question just to maybe lead it off. You said that the teachers had, you know, the positive experience of using the Magic Leap through the study, and then had an intent to use later on. But my question was, did you capture any data on how they intend to use it later on, or in what context they were interested in using it later on?
Yes, thank you for your question. They were very much interested in the applications. They proposed several teaching scenarios for the use of the glasses in their teaching. They had in mind specific subjects such as history, geography, but they all said that they need training in order to do so in the future.
Mm-hmm. Mm-hmm. Yeah, interesting. Yeah, the low social pressure within the organizational context on them, hand in hand with that lack of training and support. Very interesting. That's more of a comment. Is there other people have any other questions?
Jonathan, can I say something?
Of course.
Yes, as Georgia said, this is a pilot study.
Yeah.
This study is part of Georgia's PhD. And this period of time, we plan to continue this study with about 200 or 300 in-service teachers. And we plan to train these teachers. The training program will have 2 phases. In the first phase, teachers will create their own augmented reality objects, their own application in specific Greek school texts, books. And then we will invite these teachers to see their own augmentation with 2 different augmented reality glass devices. The first one is the Epson Moverio, and the second one is the Magic Leap. And we will compare. We try. I hope we will do to see if there are any difference between these two different devices of augmented reality glasses. And during this part of time, we did another small pilot study, and we found that we need to add in the Mara model another variable. Georgia, I think this is the immersion variable.
Indeed, the immersion variable, yes.
Okay. And if you have any ideas, because we will do this study this period, we want your opinion, your questions regarding this in order to improve this plan of study.
Yeah, the one thing that kept popping up in my mind is an old research called the concerns-based adoption model. It's Hall and Horde. I don't know if you've heard of it. It's pretty old, but kind of looking at these different phases of adoption for teachers with technology, and depending on where they are in the adoption, they have different motivational profiles. They're concerned about losing control, or they're only concerned about one particular curricular objective. And then as they go through and adopt the technology, then they get used to the technology, they understand how it's used, and then kind of move on to sort of different kinds of concerns, different types of motivations. So contextually speaking, I'm wondering if the sample that you're using, especially if you're going to have two different augmented reality devices that you're comparing, and you're allowing the teachers to customize their use of those, it might be of interest to anchor to what their specific motivations are in those curricular decisions.
Thank you.
Yeah. This is really interesting stuff. Anyone else?
I'm sorry, I forget to mention that Tassos helped us many times with this study. Thank you, Tassos, for your support. And
absolutely. Good stuff. Well, I think we've got, there's one last study here. And if we're ready to move on, if there's any other comments, discussion, questions. Really good stuff. Thank you, Georgia. Thank you, George.
Thank you.
Michael Hawley on an immersive laboratory environment for a customized learning experience. Are you ready?
Yep. I'll try to share my screen. So I hope it's working.
Yep.
Okay. Hello, everyone. Good evening from Austria. I'm Michael Holly. Maybe a few of you saw already a part of my presentation in this STEM education session. Unfortunately, I had lost my connection during my presentation because of electricity issues. So I hope it worked this time. Many thanks to join this session. And yeah, so today I'm presenting a work in progress project at the Institute of Interactive System and Data Science at Graz University of Technology. And we are working on an immersive laboratory environment for a customized learning experience in virtual reality. Teaching and learning science, technology, engineering, and mathematics are often challenging and time-consuming. Getting people engaged in science across STEM disciplines is essential. So for many students, STEM fields are uninteresting, complex, or hard to learn. To create an even more engaging and inspiring learning experience, it's important, yeah. So personalization, customization features can be used to promote motivated usage and high user adaption. In this work, we present an immersive laboratory environment for a customized learning experience, where our research focus was on exploring the motivation and learning experience of users in a customizable VR experiment room and identifying how customization features affect the VR experience. Digital learning experience that promote interactive learning and engage students are becoming increasingly relevant in modern education. Especially in STEM education, interactive simulations can be used to visualize specific concepts and help students understanding complex phenomena. To create an even more engaging and an inspiring learning experience, individualization elements can be integrated into a virtual learning application. Personalization and customizations are two strategies for achieving individualization. While customization offers flexibility, allowing users to change the content, presentation, format, layout, and navigation features, personalization includes the automatic adjustment of information, structure, and presentation to each individual user. Personalized learning paths can also enhance students' creativity and could lead to a higher level of engagement and learning outcomes. The usage of personalized content recommendation in learning systems can also increase the learning time and improve motivation as well as performance. Customization can help in fulfilling users' needs by taking their preferences into account. This gives users the ability to adapt their virtual presentation, which leads to an enhanced user experience and an increased feeling of presence and enjoyment. Adding additional customization features can further reduce the failure rate, increase user acceptance, and lead users to work more efficiently. Many popular VR games like Beat Saber or Vacation Simulator include customization features in their gameplay. For example, Beat Saber use aesthetic and functional customization features, or Vacation Simulator or a Township Tale offers the user the possibility to customize their avatars to better identify with them. For the learning application, we used the virtual laboratory environment Maroon. Maroon is an interactive virtual laboratory that allows students to explore various experiments and phenomena in an immersive and engaging way. It is implemented in Unity and supports different platforms with different levels of immersion, such as virtual reality or web-based applications. The learning activities and experiments are designed for active learning to involve students in the learning process. Once users enter the lab, this could be a physics lab, a chemistry lab, or a computer science lab. Maroon dynamically creates then the main laboratory room for the selected lab type. The main room consists of a start segment and end segment and various experiment segments. The main laboratory room consists of different experiment stations and acts as a three-dimensional menu where the user can select one of the experiments by just navigating to the specific station. This could be by moving in a predefined play area in a natural way, or by using the controller buttons to teleport to a desired destination. Each experiment or activity can then be started from an entry point that acts as a portal into the simulation room, where each experiment has a customized user interface, including virtual control elements to control experiment parameters or visualizations. The laboratory is designed as a user-friendly, engaging and immersive virtual laboratory where students can do different practical experiments. It should enhance the conceptual understanding through different simulations and visualizations. Maroon is trying to address the new generation of learners by providing immersive and engaging learning methods. To evaluate customization features in a VR learning experience, we integrated customization features into a wave simulation. It's called Huygens principle. And in the experiment room, a basin filled with water is placed in the center of the room where the user can observe the wave propagation. To demonstrate diffraction, an adjustable slit plate is put into the basin. In this scenario setting, a user can observe the experiment outcome when changing different experiment parameters. The user can, for example, change the wave amplitude, the wavelength, the wave frequency, and the propagation mode to influence the experiment outcome. Here, the drawer object acts as a control unit where the user can change the experiment parameters, the system language, and the customization features. The user can arrange the position and the height of the drawer objects to have a perfect view of the experiment outcome when changing parameters. To customize the laboratory environment, the user can change the floor, the wall material, add decorative elements and plants, or can also choose between different wall pictures and hand models. Additionally, for the wave simulation, the color of the waves, the basin, and the plate object can be changed using a color picker device. Here, the left figure shows the initial room setting, and the right figure one possible customized version of the experiment room. So now I can also show you a very short demo video of the Maroon lab. This is how the user starts. It's in a menu room where the user can just select one specific experiment or a lab. Just putting the cartridge in the slot. Then the user is teleported into the room where I can interact with the simulation, change different parameters. Currently, most of the experiments are from the physics field. Here we have this wave simulation where the user can change the slit plate, different wave parameters, and see how the interferences are shown. And currently, most of the experiments are in the field from the electromagnetic field. These are some examples of the customization features to change the colors of different objects with the color picker device, changing the floor material. Okay, for evaluating the system, we performed an A/B study with 95 students aged from 9 to 31 to compare the two different versions of the VR learning application. While participants in Group A were able to use the customization features, participants in Group B were unable. The goal of the study was to investigate the effects of customization features within a VR learning environment, to investigate how students' motivation and learning experience change. For conducting the study, we used two portable setups for the evaluation. The setup includes a gaming notebook, an HTC Vive head-mounted display with two controllers, and two lighthouses. The two setups were placed in a single classroom side by side, where each participant had a play area of at least 2 meters times 2 meters. At first, we asked the participant to fill out a pre-questionnaire that included personal information about their age, gender, and previous experience with technologies such as VR and gaming. Afterward, they were given a brief introduction to VR and how to use the controls to interact with the virtual environment. While performing the experiment, users from Group A were asked to customize their experiment room according to their preferences. After completing the task, we asked the participants to fill out a post-questionnaire where they had to rate their player and learning experience as well as their motivation. Both groups reported that the experiment was engaging and fun. They found that the VR experiment made the learning content more interesting and easier to understand. Also, there was no significant difference between the two groups. It was noticed that the participants with the customization features rated their experience slightly higher than the users from the control group. The player experience results show a significant difference in the clarity of goals. It suggests that users without built-in customization features have a clearer goal, which indicates that goal clarity is disrupted by adding customization features to the learning experience. In addition, both groups had a good challenge and immersion levels. It was also observed that participants in the customization group rated their sense of mastery slightly lower than participants in Group B. Except for one participant in Group A, all the users used the integrated customization features. Participants who used the customization features reported that they liked the customization features very much. The users disagreed with the statement that the customization feature distracted from the actual experiment. And the user mentioned that they felt more welcome, comfortable, and motivated. They reported that these features improved their experience by making it more fun. And around 66% of the users without the ability to customize their environment thought that such features would have improved their experience. In conclusion, we observed that the motivation of the users and their learning experience increased slightly when they were provided with customization features. However, the research suggests that these features had a small distraction effect from the main learning experience. Even the experiment themselves indicated that they did not feel this way. For future work, additional personalization feature and game-based learning strategies could further improve user engagement and learning outcomes, as well as the learning time. And for that, we are thinking to also add some game achievement that could increase the focus on the experiment itself before customization features are unlocked as an additional reward to motivate the user to spend more time with the experiment. Yeah, many thanks for your attention.
Fantastic. Thank you, Michael. That's very interesting. Do we have any questions in the chat? I always minimize this. Doesn't look like anybody's been chatting while I was while this was going on. Anybody?
Jonathan, yes, please.
Yes, Tassos.
Yes, okay. Excellent work. Thank you very much. Two small questions. I suppose that your simulations are real simulations based on models, yes?
Yeah, they're real simulations. They are implemented by many students. So we have a huge collection right now. We are working together also with some physics professors to really have a right simulation of the real physics.
Okay, so are there any possibilities of the students to change some variables of these simulations, for example, polarities or field intensities or wave frequencies and so on, just to study the phenomena?
Yeah,
they do
currently the experience has just some parameters, what the user can change, and then they can just observe the experiment outcome. Later, we plan also to add some task for the user. So we have already a quest management system where teachers can add some quests for the users, main quests or subquests in an XML file, which is then loaded into the scene. And then when the user did something correctly, they should get an award for it, like a maroon coin. And if they collect enough coins, they can unlock the customization features. We are currently evaluating this approach, but I have no results yet.
Okay. And the second question is, as I could say that the graphics of the simulations are more or less for young kids, for kids. But your subjects are aged from 9 to 31 or something like that. Did you have some comments from elder people, elder subjects on the graphics, on the presentation, on the interface?
The design of the...
Yes.
No, so all of them really like it. So, I mean, we are trying it also with young people and also with students. So also their feedback was quite positive, yeah. I mean, we have one project. I mean, the style is not that good because all of our developers are just computer scientists and none of us are experts in 3D modeling. But one person in our group is also an expert in 3D modeling, and he's doing a different lab, which looks much more photorealistic, and this is yeah, much more awesome.
It's not necessary to be photorealistic.
Yeah.
To learn physics, for example.
Yeah.
Okay, thank you.
And we have also the limitation because we are also providing a web version, not only a VR version, and therefore we have also some limitations for the graphics. Yeah.
Okay. Thank you.
Any other questions? Thank you, Tassos.
Thank you.
I had one more sort of I guess, observation and question to see if you feel the rightness of well, what do you think? So when you were customizing, it looked like that users were able to like change the color of the wave. Is that correct? The water?
Yeah, this is one opportunity. Yeah.
Yeah. But that doesn't have much of a change in the outcome. That just allows them to sort of decorate it, right?
Yeah. This doesn't affect the experience itself. I mean, in that case, it's just changing the color, and the other customization features is just to adapt the experience room itself, not changing the experiment.
Yeah. I'm just curious with like Nick Yee's work on customizing a person's avatar, right? The more that they're able to customize their person, I mean, regardless of whether it looks like them or not, it increases the ability that they attach emotionally to themselves. So I'm wondering if you align the customization with the actual interactions that are relevant to the outcomes, not necessarily, and I haven't figured out how that would be, so it's less of a distraction, that I wonder if it would increase their motivation. Do you understand what I mean?
Somehow.
Yeah, just so that they're not changing the colors in a way. Just, I wonder if you could align it with the actual lab environment, or make it look like your lab at home, or make it look like your lab at work. That would have an alignment with something motivational to the actual user. Whereas if you just change the color of the wave, that's trivial. So my guess is that by customizing it in a way that would matter, would increase their motivation.
Yeah, I think you're totally right. I mean, it was just a starting point.
Yeah.
May I jump in?
Of course.
Okay, thank you. Our previous empirical research on teaching and learning physics principles by using virtual and augmented reality show that the design of the physical magnitudes or experiments doesn't matter. We have to pay attention in physics, and the simulations, they have to work correctly.
Right.
Yeah.
This is my opinion.
Yeah, absolutely. Yeah, it's a matter of like hooking the agency of being able to change the environment in a way that actually connects to the interactive, the goals themselves, I guess, in a way. That seems like it would influence engagement and motivation for.
Yes, that's right. Yeah.
Really cool stuff, though. This is really great. Good work. Any other questions or comments? Well, I think this concludes.
Thank you again for the opportunity to do the presentation again.
Oh, absolutely, Michael. And please
so sorry.
Say hello to Johanna for me. Yeah, happy that we could do it. I know that was pretty stressful for you to lose your power there.
Yeah, it was a very stressful situation. Yeah.
Yeah.
But thanks to all of you, for this organization. Yeah.
100%. And thank you to the rest of the panel, or of the session members for being so gracious and making room for Michael as well. This is great.
Yeah, thank you.
Great community.
Okay.
All right.
Really cool session.
Yeah, this was fantastic. This is the foundation, the meat and potatoes.
Yeah, that's it. Yes, yes. Okay.
All right. Well, thank you all. And
thank you.
The session can record or finish now. And I will see you all around the conference.